Okay. Okay, so today I'm going to talk about geodesic rays and the Donaldson-Uhlenbeck-Yau theorem, mentioned by Julian. So this is based on some joint work I did recently with Matthias Jonsson and Sonal Shivaprasad, both of whom are also here at the University of Michigan. So let's start maybe with just some setup, introduction. So the setup here that I'm going to consider is I'm going to consider a holomorphic complex manifold. So this is a complex manifold. And n is going to be the complex dimension for me here. So it's a real dimension to n. And really, I'm going to want this manifold to be Kahler, but I'll explain what that is in just a sec. So the real interest here, the real object we're sort of interested in, though, is going to be holomorphic vector bundles over X. So
Nick, can you talk a little bit louder, please?
Oh, yeah, sure,
it's not your fault, but it's a system here which is a bit low.
No worries. Yeah, I can try and speak. Just let me know if I'm not speaking loud enough.
Thank you.
Okay. Yeah. Okay. So I'm going to be interested in holomorphic vector bundles, E. So the rank here will be R for later on. So it's a subject of great interest in Kahler geometry, and sort of complex geometry more generally, to study the existence of certain positive Hermitian metrics on these vector bundles. So that's just going to be a fiberwise metric compatible with the complex structure. And to give you maybe sort of some motivation for why we like to consider metrics, sort of these special metrics, let's just quote maybe a main sort of a theorem, although it won't really have to do anything with the actual talk here. So this is really just a motivational theorem to give you sort of an idea of why we care about such things. So this is a classical theorem of Kodaira. It's the Kodaira embedding theorem here. And it tells you that if R is equal to 1, so E is really a holomorphic line bundle, then E admits a Hermitian metric with positive curvature if and only if you can use sections of E to embed the manifold X into projective space. So if and only if you can embed X in some large copy of the complex projective space using sections. So this sort of gives you a relation here between a metric property, so this positive curvature property here, and a very concrete geometric one. So being inside CPN is very restrictive for a number of reasons, mostly coming from algebraic geometry. So any complex submanifold of CPN is automatically going to actually be algebraic. So it's actually going to be cut out by polynomials. It's a zero set of a bunch of polynomials. So really you're passing from just the analytic structure here on the one side to a stronger algebraic structure on the other side. And so this is sort of maybe one theme in the field really is relating analytic properties with algebraic ones, which are sort of maybe a priori stronger seeming in some sense. And so the specific instance of this that I want to talk about today is going to be what are called Hermitian-Einstein metrics. So let's make a definition of that. So the specific things I want to talk about today, I'm going to say that a Hermitian metric on E is what's called Hermitian-Einstein. Maybe Hermite-Einstein is here. If the curvature form theta of H satisfies the following differential equation here. So if I take the trace of this form, then I'm looking to get a constant. So maybe I should explain some of these things real quick. I apologize. I got ahead of myself slightly. So the curvature form, the way I'm going to think about it here is I'm going to think about it as an endomorphism valued 1-1 form. So maybe an endomorphism valued 2 form if you're less familiar with the complex world. So if I were to write theta locally in holomorphic coordinates, so maybe my holomorphic coordinates are zi, and I write theta locally, it's going to look like a bunch of endomorphisms R parameterized by 2 indices I and j bar, and then times a differential form that looks sort of like this. So this is sort of generically what the curvature is going to look like. And so these R, I, J, these are endomorphisms. Okay. And then I should have said this before, and I apologize, but omega here I want to view as a fixed Kahler metric manifold. So a Kahler metric, if you don't know, it's a special type of Hermitian metric. It's a closed positive 2 form. And this is just maybe some trick to encode the Hermitian structure on it. So if you want to look at this in local coordinates, you can also do so. And it looks sort of like this. So you have a metric, which in this case is just a Hermitian matrix, positive definite Hermitian matrix. And then you have, once again, a form sort of looking like that. And I'm going to view this omega as fixed, and H is the actual metric I'm interested in. So I should have, H is the metric that we're looking for. And then otherwise, the other 2 things here are maybe a little bit less relevant here. C is just some constant in R, and then identity E is, of course, the identity. Okay. So sorry for the forgetful setup there, but this is the equation we're sort of going to be interested in here. So we're going to be looking at the trace of this curvature form, and we want this to be a constant. So if you happen to be a differential geometer, which I don't think many of you are, but if you happen to be, the idea, of course, is that the trace of the curvature looks sort of like the Ricci curvature, right? So if you were really working with the Levi-Civita connection on the tangent bundle, you would really say the trace of the curvature is the Ricci curvature, and that's where the name Einstein comes from here. So this really sort of looks like the Ricci curvature in some sense as being constant. That's maybe the motivation for the name. Okay, so let me pause and any questions just to make sure I haven't botched things too badly. Okay, so that's the objects we're going to be interested in today. And so the theorem that's going to relate these to an algebraic condition is a really famous theorem from the 80s due to Uhlenbeck-Yau, building on some pretty fundamental work of Donaldson. So the theorem is usually referred to as the Donaldson-Uhlenbeck-Yau theorem because of that. But it also goes under a couple of other different names. I know sometimes people refer to it as the Kobayashi-Hitchin correspondence. Those 2 sort of separately are maybe responsible for formulating it sort of closely to the way that I'm going to state it. And the statement is going to be that the vector bundle E admits a Hermitian-Einstein metric if and only if E is what's called slope stable. So slope stability is going to be sort of my algebraic condition. And there's not a super clear embedding type statement that I can make here. So I'm going to postpone the definition just slightly here to let you see what the statement is. And maybe I should have given you some dates. This was proved, I think, in 85 and 86, where these papers came out. Okay. So slope stability is really an algebraic condition, sort of like I mentioned here. It was studied by Mumford. I believe in the sort of idea to look for good moduli spaces of vector bundles. So I think he realized when moduli theory was sort of in its infancy, he realized that this condition here allows you to construct a good moduli space of these bundles. And so now maybe let's give the definition. So slope stability is phrased in terms of subsheaves inside the bundle E. So I'm going to let F here be a holomorphic, torsion-free subsheaf. Maybe I want it to be proper too. And maybe I should have assumed at the start, this is not important, but probably wanted my E to be irreducible. But anyway, so slope stability, I have this subsheaf. And so now I need to define what the slope of the subsheaf is. So to define the slope, it's really sort of an intersection theoretic number. So first thing is I want to consider the first Chern class of F. Here. So you can think about this as some element in H2. Let's just say like that. And then the slope here is going to be the integral over X of the pairing between C1 of F and omega to the n minus 1 divided by the rank of F. So this top number is usually referred to the degree. It corresponds to the trace that we saw before, right? So another way to represent this, if you will, so just maybe a remark to relate this to the previous condition. C1 of F, if you suppose F is maybe an actual subbundle, so maybe this makes a little bit more sense. If it's actually a subbundle, then you can represent C1 of F, the curvature of any Hermitian metric subbundle. So if I represent this first Chern class by a curvature form, then this quantity looks like curvature form, wedge omega to the n minus 1, which is up to multiplying by volume form, the trace. So this is sort of the trace. So this is just an identity. So the slope here is measuring, in some sense, the average of the trace of the curvature. That's maybe how you should think about this. So this is my definition of the slope. Now, what does it mean to be slope stable? So E will be slope stable if E has the greatest slope among all of its proper torsion-free subsheaves. Oh, what happened there? If the slope of F is strictly less than the slope of E. Okay. Any questions?
And in general, this really needs to be checked on subsheaves, right? Not only subbundles.
That's correct. I forget exactly when. I think if your base manifold is a curve, it suffices to consider subbundles. But in dimension 2 and higher, you really need to check it on subsheaves.
There are counterexamples in the mentioned.
Thanks.
Okay, so this theorem has been hugely influential in a number of areas. So, I mean, I would be remiss not to talk about maybe just a few of the names who have worked on it, but I won't quite go into detail about writing them down. So for now, let's focus on maybe the people who came before Donaldson, Uhlenbeck, and Yau. So there was sort of very fundamental work due to Narasimhan and Seshadri. And then this was again followed up by Kobayashi and Hitchin, as well as Atiyah and Bott, and Bogomolov also. So these were all sort of fundamental in formulating the exact statement of the theorem. And then again, it was proved by Donaldson and then Uhlenbeck and Yau. And so Donaldson sort of gave a complete proof for projective manifolds, but Uhlenbeck and Yau sort of did their proof separately, and it worked for any Kahler manifold. So a defining thing in their proofs, in both of their proofs, is that they're very hard, especially the Uhlenbeck-Yau proof. It involves a complicated, I mean, it's not, the idea is maybe not super complicated, but the analysis behind it ends up being very complicated. So very briefly, what Uhlenbeck and Yau do is they take this equation here and they sort of smooth it out. They replace it by an approximate equation by introducing a parameter epsilon. And so this approximate equation, they show that you can always solve regardless of any assumptions on E. And then when you let the parameter E go to 0, you will only get convergence of the solutions to this approximate equation to the actual solution when the bundle is stable. And so it's a very delicate procedure. Extremely fundamental in geometric analysis in general, but very difficult and very hard to follow. And I think it doesn't use stability in a way that sort of makes intuitive sense from the point of view of the problem. They sort of just use it to boil down to getting they show that when you're stable, you can get some sort of a C0 estimate. And then, okay, then that's enough to make sure that whatever they converge to is actually a solution and not some, singular object. So it's desirable from several points of view to have maybe a better, more conceptually clear picture of the theorem than the Donaldson or Uhlenbeck and Yau proofs. And so that's sort of maybe the idea behind our work, but also we weren't really the first people to come up with this sort of desire, certainly far from it. So maybe,
sorry, in this
yes.
context, is there some characterization for slope stability by quotient bundle?
By quotient, yeah. I mean, so I will need to talk about quotient bundles in just a sec. But if you look at the quotient of E by F, there's the Chern class is split. And so the slopes will also sort of split in the same way. So if maybe I call this G, then slope stability is the same thing as asking for the reverse inequality, that mu E is less than mu G.
Okay, thanks.
Yeah, you're welcome. Yeah, things will naturally be stated a little bit more cleanly with respect to quotient bundles anyway. So this will show up in just a sec. Okay. But so sort of the goal of our work, and again, work preceding us as well, is to maybe give a sort of more conceptual proof of the Donaldson-Uhlenbeck-Yau theorem. So before I can actually sort of explain what the actual proof is, I think I want to move a little past theorem in time and move forward to something that was greatly influenced, I should say, by the Donaldson-Uhlenbeck-Yau theorem itself. So let's move forward a little bit in time, and then we'll come back to discussing the goal here. And so I'd actually want to talk about right now another conjecture, which is sort of now solved. It's known as the Yau-Tian-Donaldson conjecture. So then there's sort of a nice interplay of ideas here that we'll sort of see in just a sec. So the Yau-Tian-Donaldson conjecture, the basic idea is you want to take the Hermite-Einstein equation here from before and then replace E being an arbitrary holomorphic vector bundle with really the tangent bundle of X itself. Okay. And then the question is going to be, instead of just looking for the metric H on E, you want to also look for the Kahler metric omega. So you want to solve for omega and H simultaneously. Right, and this is possible because you're going to really actually set them equal to each other because E is the tangent bundle. So now this is going to turn your equation from before, which previously was a trace, into something much more complicated. It's going to become a determinant. So this is going to turn the HE equation into what's known as the Kahler-Einstein equation. Sort of this trace of the curvature is going to be replaced with the determinant of the curvature, which maybe I'll just leave writing as omega here, somewhat improperly. Okay, so the setup is vaguely the same. I mean, in the sense that it's coming from the same equation, but you're certainly replacing it with a much harder equation, right? So the trace is, it's not actually truly a linear equation before, but it's maybe quasi-linear. This equation is completely nonlinear. So you're going to have a bunch of determinant derivatives mixed up with each other. So the equation is much harder to solve. But there was still sort of some hope that there should be a stability type condition relating solvability of this PDE, determining solvability of this PDE. And that was the Yau-Tian-Donaldson conjecture sort of now solved. So this is really a theorem now due to Chen-Donaldson-Sun. Well, with some work of Tian as well. And so it really says, maybe abusing some notation slightly, that X admits a Kahler-Einstein metric if and only if the tangent bundle is K stable. So we won't actually need to define K stability here, but I want to show you that there's a similar theorem. It's sort of in the exact same spirit. It was proved much later, deeply influenced by the Hermite-Einstein picture. Now, because of the more formidable analytic techniques that were present in this problem, people were definitely not able to follow the Uhlenbeck-Yau or the Donaldson approach. And so if you try and copy those, they will fail quite miserably. And so you have to be, I mean, that's why there was such a gap in between proving these two things, right? There's almost a 40-year gap. I guess maybe closer to 30. But so the point is, because of this, Chen-Donaldson-Sun, I mean, they came up with a very clever argument that maybe I wouldn't say is the most intuitive, but people still beyond that were maybe deeply interested in finding an intuitive picture, and this has been around and attracted more interest. And so there's sort of eventually did come to be maybe a bit more of an intuitive picture. So this is sort of what's called a variational approach. And in this context, it's due to Berman, Buxbaum, Jonsson. And so this will sort of maybe be the intuitive picture that I think we're going to be after here. So let me describe it in this case, and then I'll move back to the Hermite-Einstein case and sort of show you how it appears there. So the idea is to consider looking for your Kahler-Einstein metric inside the space of all Kahler metrics. So I'm going to let here H be the space of all Kahler metrics. And so this is maybe some gnarly space. It's some infinite dimensional space, but it turns out it's not the worst space in the world. There's some sort of a formal Riemannian structure that exists on this space. So it sort of admits a formal Riemannian structure. And so in particular, I can talk about geodesics inside this space. So it turns out, I have my space H, and I can look at geodesics. Right? So this sort of gives this infinite dimensional space a nice, almost, Banach type feel. Really, it's some sort of a Frechet space, if you will. And so what you can end up doing then, this was done by Mabuchi, you can write down a functional M. So this is called the Mabuchi functional in this context. Here, which is going to be convex along these geodesics, and whose minimizer are exactly the Kahler-Einstein metrics. So this functional, okay, that's sort of great. This is sort of why you get the term variational here, right? So you're looking for minimizers of maybe some sort of an energy. If you are perhaps familiar with maybe a more classical argument, so suppose you wanted to solve the Laplace equation, you would minimize like the Dirichlet energy, and that's sort of the root idea of this. And so M here is some sort of nonlinear analog of maybe the Dirichlet energy, if you will. And so now let's sort of think about this maybe a little bit more impressionistically. So the question of solvability of the PDE should come down to whether there exists a minimizer or not. So the question sort of just reduces to, do these things exist? And if M is convex, sort of along geodesics, well, we can maybe even further simplify the problem. So maybe let's consider this as a geodesic here. And M is sort of a convex function. So maybe this is my endpoint here. Maybe I should draw it a bit longer. So it'll certainly have a minimizer if the slope of the convex functional, sort of at infinity, is positive. And conversely, if the slope at infinity is maybe just trailing off to 0, or even worse, becoming negative, you would expect there to be no minimizer. So you sort of get a nice dichotomy in some sense. You'll see that the slope sort of at infinity should determine existence of minimizers. Okay. So that means instead of really looking at geodesics, what I want to do is I want to look at sort of infinite geodesics. I really want to look at geodesic rays, and I want to study the behavior of M as M moves out along this ray. So I really want to look at the slope of M, which you can measure by sort of taking the limit of maybe something like this. My geodesic ray is omega t. I divide by t, and I look sort of at the limit as t goes to infinity. So this is really using convexity of M here. This is sort of my asymptotic slope along a geodesic ray. Okay, so far so good, but I haven't really shown you where the stability should come in. And so the actual place the stability comes in now is maybe a bit clever here. It actually turns out that the stability is related to exactly which rays exist in some sense. So that's sort of maybe the idea here. So I didn't say this, but maybe I can recall it now. So in slope stability, you were checking subbundles or subsheaves, sorry, of E. For this K stability notion here, you replace these subsheaves with what are known as test configurations. doesn't really matter too much what that is. But the point I wanted to make here is that there's really sort of a nice dictionary between test configurations and rays of Kahler metrics, geodesic rays of Kahler metrics. Okay. And then the slope stability, the slope itself will sort of become apparent as the asymptotic slope. And maybe that it's not actually an accident in some sense that the word slope appears here in both contexts. Okay, so that's sort of maybe the picture here in the Kahler-Einstein world. And the idea was to try and take this picture, which is sort of nice and conceptually clean, and transport it back to the Hermite-Einstein problem. And so the answer to our goal in some sense is to transfer this variational approach to the Hermite-Einstein setting. Okay, so any questions before I continue on? Okay. So this is sort of going to be this sort of cleaner approach here. And so we were not the first people to do this. Really, the first people that I know of to do this were Hashimoto, so both of whom are in the audience, I believe. I think I saw Yoshi on the Zoom here. So work of Hashimoto and Keller. So in 19 and 21, perhaps here, they sort of give this approach a go. And the way they do it is going to be pretty different from the way I'm going to do it, but it has some nice merits on its own. I'm not really the expert here, right? So I guess they're the experts here. But briefly, what they do is instead of looking at geodesic rays and sort of a big space of all the Hermitian metrics like I'm going to do, they sort of want to try and take a more finite dimensional approach here. So they want to look at sort of geodesics in a finite dimensional space, and they really sort of want to look at geodesics in I think their metrics on maybe sections of E tensor with some large power of a line bundle L here. And so the idea is this gives you a nice finite dimensional space. So these give you some sort of nice finite dimensional approximations to maybe what are sort of larger geodesic rays. This is very similar to some of the work in the K-stable case here. And it has its own merits, right? So it's certainly very nice. The finite dimensionality is very nice. And so this is a very nice set of works here that they have. And so what we decided to do is we wanted to maybe bypass the finite dimensional argument entirely. I think we kind of wanted to, instead of doing it like this, where they're sort of doing like Bergman approximations, maybe Bergman. We wanted to instead maybe look for sort of an analog of what are known as like a finite energy rays, something like this. So that was sort of our goal here. So this is maybe trying to say that we were looking at another side of the same coin in this setting. So we're trying to look for geodesic rays in really the space of Hermitian metrics on my E here. So back to this E or here. And so there is a way to do this that has sort of been known for a very long time. It's a very classical way to write down these rays, and it's actually very simple. It's much simpler than in the Kahler-Einstein setting. So it turns out if you take any two metrics here, H1 and H0, you can form a geodesic between them, HT, by looking at e to the t, what I'll call, maybe let's call it lambda, H0. where lambda is really just this log of h1, h0 inverse. So this is log of a matrix log. So it turns out this just works. It gives you a nice geodesic, sort of with the formal Riemannian structure here. And so this sort of gave us our approach to what we sort of wanted to do, okay? So we're going to look at geodesic rays then. The form e to the t lambda h naught, where h naught is some fixed guy, maybe our starting point, and lambda, as you sort of can see up here, it's going to be an endomorphism of E, and it's really sort of going to be a trace-free endomorphism. It doesn't really need to be trace-free, as I'll mention in a sec. And so one important thing that we're going to consider here, so like whenever you're doing these variational problems, right, in order to find a minimizer, you're usually going to be interested in some sort of a compactness statement. You're going to need some sort of compactness statement in order to say that you have a minimizer. And now the space of smooth functions is not really compact. You kind of want to pass to a weaker space where you have some sort of nice compactness results. So some sort of a Banach space. And so the space we're going to actually pass to here is we're going to need our endomorphism to be maybe W1P. So this is a Sobolev space. So the first derivative should be in LP. Okay, and this is so that way we can actually sort of guarantee that we have minimizers. Okay, accepting that though, the main sort of result that we're going to get is the main thing that was sort of missing in the previous picture is some sort of way to go from a geodesic ray to one of the objects we're testing against. So we really want to move from geodesic rays and sort of build a dictionary between those and sort of sub-bundles or sub-sheaves. So the goal for us, maybe this is our main results, maybe I'll state the results maybe more specifically here, is to build a dictionary between geodesic rays, possibly singular in the sense above, and subsheaves of E. That's going to be sort of our main goal. So any questions before I sort of start stating things?
How do you choose P?
That's a good question. So maybe I won't write too much about this. It's not actually clear to me what P should be at the end of the day. So we have a couple different P's floating around. So in one direction of our correspondence, we can take P to be infinity actually, or maybe P any number, not infinity. But then if we're going to go in the other direction, we're sort of going to need to actually use the Sobolev inequality, like the normal one. So the normal Sobolev inequality for one derivative. And so this P that we get ends up being the P from the Sobolev inequality. So like the Sobolev embedding theorem gives you a natural P. So W1N, maybe I should say here. Sorry, my brain left me. Right, W11 here is going to embed in a certain LP determined only by the dimension. And so maybe I'll call this like P max or something. So at some point, we're going to need to consider P less than P max, but I'm actually really not convinced that P max is the right P. I think actually you can take P to be anything. I think you can take P to be anything less than infinity. Okay, so let's state the first part of this dictionary. And so this is maybe why I'm convinced that P can be sort of anything. So this is maybe our first theorem here, and it's going to be in the direction from a subsheaf to a geodesic ray. So if I'm given subsheaf here, then there exists a geodesic ray in, so maybe let me write the geodesic ray of this form, e to the t lambda h naught, with lambda in W1 infinity. So it really will be, the first derivative will be bounded with the asymptotic slope along this ray. So if you look at the asymptotic slope here, you really get mu of G, mu of E times the rank of G, where here G is this quotient sheaf. And so here, really, you see the sort of the direct relation with slope stability, right? So the slope stable condition phrased in terms of G is that this quantity needs to be positive, right? So this is sort of slope stable. Okay, I'm gonna sort of very briefly sketch the proof here. So the proof is actually a very nice direct construction. It's actually surprisingly explicit. So for the moment, let's take F to actually be a subbundle here. And in the general case, we're actually just going to resolve the subsheaf by blowups, and then we'll just sort of reduce to this right here. So, but in this case, when it's a subbundle, what you can do is you can identify G with a subbundle of E. So you really identify G with the orthogonal complement of F here, sitting inside E. And so you can take your starting metric, H naught here, and you can decompose it into a part on the subbundle F and a part on the subbundle G. And then you'll get some junk here, which I don't really care about. Okay. And now the idea is, okay, in the limit here, as t approaches infinity, I really sort of want to see the slope of G appear. So I really want this G term to be contributing sort of in the limit. So what you want to do is you want to construct metrics that sort of just look like this. And this is actually just the geodesic here. You kind of just do this. This will be our geodesic ray. Sort of just keep magnifying the HG part. And okay, so if you compute from this what lambda is, lambda will actually be smooth in this case. So lambda is always going to be just the identity here, sort of this diagonal matrix. And it's going to be a smooth endomorphism in this case. So, okay, you have to do some work here. Really, all of the work is in making sure that the computation works out here when you try and compute the curvature of this guy. So when you try and compute the curvature of this guy, you can do so, and it's really kind of a little lengthy here, but what you end up getting is a curvature of this form here. So you get almost the curvature of the original metric here, sort of split among the two, and then you get some sort of exponential decaying term. That doesn't really matter here. So this is some decaying, exponential decaying term. And now what you can do is you can look at the Donaldson functional. So the Donaldson functional, I didn't say this, I apologize. this is the variational functional in this context. But if you look at this here, it has a pretty nice formula. So it's just the integral of the average of lambda times the curvature of ht, wedge omega to the n minus 1. Oh, maybe I should have. Yeah, just like that. That's fine. And then you integrate it with respect to s. So maybe this is something like that. Okay. So if this is your lambda that you've computed above, this is the curvature you've computed. Well, you can see that this star term here, which I didn't write down, it doesn't matter when I do lambda times the curvature. So sort of what you get out. Oh, I'm sorry. One sec. Right. So sort of what you get out when you compute this is this trace here, when you average it out, is it's just the average of the trace of G. So it doesn't depend on T at all. So you get T times the rank of G times the slope of G. So this is the degree here, and so I'm just multiplying by the rank. And I did forget one additional term in the Donaldson functional. Usually this disappears when you're working with trace-free endomorphisms, but my lambda here is obviously not trace-free, right? So it has trace to it. So you do get one more term here. It is the following minus this constant from the Hermite-Einstein equation here, trace of lambda. So you get this correction term here, but the correction term ends up being, sorry, H naught. So the correction term now is you get this extra T rank G, because you have the lambda here, slope of E. You get the E from this guy.
There's also omega n minus 1 somewhere on the left.
Yeah, I think I've written this down a bit poorly here. So if I had chosen to rewrite this slightly differently, if I had written it like this, then that would have been more correct. Ah, right. Okay. Sorry. My notes were actually right. I just thought they were wrong. This is what it is. I apologize. And so it's this C here. This C is from the HE equation. So it's cohomological. So it's just when you write it out, it ends up being the slope of E over some like 2 pi n or something like this. Yeah, so this is the right thing. I apologize. I think my notes are slightly off. Yeah, sorry about that. But that's sort of all you need to do in some sense. It's sort of just a computation at the end of the day. Maybe I want to wrap this up. So I would like to move to the second part of the proof. Okay, right. So where does the singularity show up? Okay, so this was the case of a sub bundle. If you have a subsheaf, you just resolve it. So you really just take the subsheaf, you do a smooth resolution, so you blow up smooth centers, so you can pull it back to a sub bundle. You do the computation upstairs, and then you just push it down. So when you pull back, none of the slopes change as long as you are happy working with no longer a Kahler metric. When you pull back your Kahler metric, it's maybe singular along the subvariety that you've blown up, or the exceptional divisor above it. But you can still work everything out just fine. So things still sort of work out in this construction. It's just when you push it back down, now you're going to get something that's smooth outside of the locus that you blew up. But it turns out pushing down doesn't do anything. It doesn't change any of the blow up behavior or anything like that, because you're sort of only interested in first derivatives. So everything that was bounded above just remains bounded when you push it down below. And that's why you get this W1 infinity here. And you don't get anything worse.
So
So-
the proof, the
Mhm, go
proof
ahead.
will work for torsion-free
Yes, yes.
sheaves, right? For it, not only a bundle, but for a general class.
Yeah, so if F is torsion-free, sort of, you look at a resolution, X tilde over, maybe I should write it like this. So you have your subsheaf over here. You sort of resolve it to a subbundle by some map pi. With some blow up. So there's some way to do this. It's outlined in Jacob's paper. It's sort of, I think originally the idea for how to do this concretely is due to Bando and Su, but they didn't perhaps write it down very carefully. They sort of just do it in some sense. Jacobs does a bit of a better idea, a clearer explanation.
But I mean for E also torsion-free.
Oh, I'm sorry. Yes, it should also work there as well. We did not carefully check that case. So let me put that as a disclaimer. But it should work just fine.
So you should be able to get an analog of the result by Bando and Su then.
Yes, you should. You should. I think the question is maybe you want to be a little bit, you want to agree with what you want to settle on what you mean by a singular metric, just to make sure that there's no confusion. Yeah. It definitely does not work though for a singular manifold X. That's the one thing I want to be clear on. E should be okay if we let it be singular, but X can't be. Okay. And then how much time do I have actually?
5 more minutes.
Okay. Yeah, let me just then state the other part of our theorem, which is just the reverse direction here, because this is a bit more restrictive. And here we really do need to use at least one of the results of Uhlenbeck-Yau. So it's not entirely free of their results, but it is free of their complicated continuity argument. So the theorem is the following. So suppose we have a weak geodesic, sort of this form here. With here's where I need the slightly, well, actually, it doesn't really matter too much, but I need something like this here. I also need to assume, though, that the asymptotic slope along this geodesic is strictly non-positive. I really need to assume that I have an unstable geodesic already. Once I have this, then we can show that this sort of geodesic comes from a construction like the above. So specifically, instead of finding just a subsheaf, we find a filtration of E by perhaps subbundles or subsheaves, I'm sorry. Here. And if you have something like this is enough to sort of repeat the above construction. Maybe you change the details a little bit slightly, but it's more or less the same construction. But you show that once you have this negativity condition, you really do get a filtration here. And then the negativity sort of corresponds to one of these being unstable. So there exists a filtration with at least one unstable. So the proof of this is, it's a bit more technical, but it's not too bad at the end of the day. The actual most technical part in our proof is, I'm gonna skip it entirely even, but so the way to see this is you actually sort of have to rewrite W omega, sorry. You have to rewrite the Donaldson functional to be more clearly mean, so it's clearly defined for what you actually want here. So if lambda, I'm sorry, in the paper we call this W, but it looks too much like omega when I write it, so I switched it to lambda. So if you take this lambda and you diagonalize it here, and then you look at the first derivative of this, which is still fine, you're going to get a bunch of 1-1 forms, sort of like this here. And it turns out there's another way to define the Donaldson functional of this purely in terms of these guys, so you don't have to refer to the curvature. So if you do that, it looks sort of like this. It looks like sort of a weighted W2 norm for these components of the first derivative. And the key point here is you have this exponential decaying term. You get some other terms here. The key point is this exponential decaying term here. And the point is, okay, if my asymptotic slope is negative, like I've assumed here, this exponential term has to sort of be 0 whenever the difference between these two things is positive. So just the fact that the slope is negative implies that this first derivative is strictly upper triangular, strictly lower triangular, sorry. And in particular, it has zeros all along the diagonal. And so now if you compute what these zeros are, so it turns out whenever you have one of the diagonal elements in here, it really is the same as taking the derivative of the corresponding entry in lambda. So this being 0 implies that these really are constants. And so this endomorphism I started out with sort of clearly looks like it's going to be defining a filtration, right? So the fact what you're going to do is your filtration is going to just be the subbundle corresponding to the fixed zetas. Okay, so that's not obviously holomorphic. So this is why you sort of need to use Donaldson or Uhlenbeck-Yau's theorem. If it were holomorphic, this would be truly 0, but Uhlenbeck and Yau sort of show that this condition of being lower triangular is enough to conclude that actually it really is 0. So there's sort of an argument that goes on there. But that is maybe my time. So sorry. Thanks for listening.
Okay. Are there questions or remarks?
I have a question regarding the analogy with the Yau-Tian-Donaldson conjecture. So in that setting, there is there is one side of the conjecture that is very well established, namely the existence of CSK metrics, let's say, and the properness or the coercivity of the K energy.
Yeah.
And then there is the other direction, which is not as well understood, which is the connection with K stability instead. So so roughly, and at least in my understanding, the relation between these two things is that K stability predicts that actually to check coercivity, you only need to check it along some rational geodesics, sorry, some rational rays somehow. So is there a similar thing here, or it completely, or is everything so explicit that actually you don't have a distinction between the algebraic stability and the analytic one?
Yeah, that's it. Sort of is so explicit here that I haven't seen a distinction. The one thing of note that still like confuses me a bit, right, is really in this theorem we do need these negative rays, right? So I mean, if there is something dealing where secretly like you only need to check rationality or something, I think somehow there's maybe another way to do it other than with just this negativity, I guess, in some sense. But at the moment, at least, everything here is so explicit that we never need to use any sort of rationality assumption or anything.
Okay.
Yeah.
What about semi-stability? What is happening?
Yeah, no, that's a good question. I think there should be something you can do with semi-stability. It really feels like you should be able to adapt what we do to the semi-stable case. The problem is, it's again right in this exact argument. When you do when you remove this and you ask for something that's strictly less than 0, I've not been able to leverage that into getting a better, like a strictly unstable E. So really, it's improving this somehow.
So you say that it's not clear that you can sort of degenerate your bundle to a splitting into subsheaves, into stable subsheaves.
I mean, okay, so the way I'm thinking about it, at least, is if this is a strict inequality, you want one of the elements in your filtration to be strictly destabilizing, right? You really want a strict inequality between the two.
Oh, sure.
Yeah, and that doesn't seem to pass through in the argument.
Okay, thank you.
Yeah.
Okay, so maybe I have a question. If you take a subbundle of E, for example, and E is a vector bundle, and this subbundle is stable, semi-stable, or stable. So slope stable.
Sure.
For example, we take the maximal destabilizing subbundle. So by Yau-Uhlenbeck-Yau, so the metric is Hermite-Einstein, right? So how this metric is related to the metric of the original bundle? So
how is it related to the metric you started with?
yes.
I'm not sure that there should be like maybe I'm missing something, but I'm not sure that there should be a relation. Maybe I've misunderstood your question.
Okay, thanks.
Yeah, sorry.
Yeah.
Last question.
Oh, yeah.
Yeah, please ask question.
Can you hear me? Can you hear me? I think you
Yes.
can hear.
Yeah.
Yeah. So I actually have two questions, and one's pretty technical. So in the last part of this second proof, so it can happen that the destabilizing sheaf may not be a vector bundle. It can be just a sheaf. In that case, maybe the constant that phi a these constants in the last line of your proof.
Yeah,
they're meant to be constants only on the outside of the Lebesgue measure zero set, and then okay, and then the
right. So I mean, like these are 0, but really they're sort of zero only at best in like the L infinity sense.
Mm, mm.
And so that it's not actually technically right to say that they're constants everywhere. You can
Mhm,
sort of only get that they're constants on some
Mhm.
Lebesgue measure one set. So yeah, definitely that can happen. It does happen. It's not actually ruled out here. Yeah.
Yeah. No. So I was wondering that so you worked with this W1P Sobolev space, but do you think it's kind of essential to allow similarities for these geodesic rays? Because I mean, as you said, the geodesic rays in vector bundles can be, you can take a smooth one. Now, for
Right.
the
Yeah.
the reason why you need to think about similar ones is that the geodesic, there are
There are
similar geodesics which doesn't have any vector bundles. So do you think it's kind of essential feature of your work that it's W1P, or do you believe it can be sort of improved to
that's a really good question. It seems necessary to have the singular guys because there doesn't seem to be a way, at least for us, to encode the subsheaves. So like really, whenever you have a subsheaf, the best we could say that we get the ray is W1 infinity. We sort of tried to construct local models to see if that was really the case.
Mhm.
And it didn't look like it. That's about the end. Like nothing definite, but it didn't look like it. So it really did look like we did actually need to enlarge the space to these W1 infinity rays at least.
I see.
That being said, I don't think you actually need to go to a larger space. I don't think you really need to pass to that larger space. I mean, certainly if like every ray, I mean, if every subbundle gives you at worst a W1 infinity, you shouldn't think you need a bigger space. And
Mhm.
really like the W1P, I know it didn't show up today in what we were doing, but it shows up in the way we need to prove properness. Like we actually sort of, the way we measure properness is via this W1P Sobolev norm.
Mhm.
And basically the idea is that control of the Donaldson functional is sort of like an inverse Sobolev inequality. Bless you. So it turns out that if the Donaldson functional is finite, then you don't necessarily get that your W1 infinity, you get your W1P in this certain P that sort of shows up in the reverse Sobolev. And that appears to be stable. There was no way to leverage that into like a Moser argument that I saw at least. So I mean, yeah, it's just at the end of the day, what we have is a very basic estimate. I would be surprised though if there's not a better way to improve what we have to actually get some better coercivity control.
Thank you very much. Very interesting. Thank you.
Thanks. Yeah.
I have a small question.
Okay. Yeah. Real
So
quick.
if the Donaldson functional is proper, is the
Mhm.
coefficient of the properness, I mean, how properness it is relates to
Ah.
anything? Like
That-
in Babuchi is related to alpha or delta invariant. Is it related to anything here?
Yeah, that's a good question. That was something we were exploring, but we didn't get very far in. So I don't know. That's that's my answer.
Okay, thank you.
Yeah, I would be interested to know though.